But first, we're going to talk a little bit about functions. So, dang, what's up with this? Okay, so a function, a complex function, has the domain is part of the complex numbers, and the range is also part of the complex numbers. The codomain is the complex numbers. Okay. Here are some examples of how you can do that. So there's three, those are the first three examples. So you could have, so this right here is saying that we're using z as the complex variable. So that's x plus iy. So z is x plus iy. And then we have these expressions right here in z, okay, on how to do it. So your input variable is z, and then these outputs are in terms of z. Okay, so this is one way to express functions, complex functions. That's one way to express complex functions. We're just with the z. Okay. Another way would be if you have it like this. Well, there's actually two different ways. So these are other ways. Okay, so instead of putting a z right here, just having a z, you have x and y. Now you could also, another thing, you could also have just a z there, but then have these x's and y's in the expression. So another way is to just write it in terms of x and y's instead of writing in terms of z's, or even writing in terms of r and theta, r and phi. Okay, so because you remember z is equal to r e to the I phi, right? That's another way of writing that. So this would be the r and the phi would be from the domain part. So that's another way of writing it. Okay, so they're saying that's different. There's different ways of writing it. Okay, then right here, this first definition is important. This is the definition of a limit. A limit. Given epsilon greater than 0, we can find a delta so that this implies this. Okay, so let me rewrite that a little bit. So given epsilon a positive number, there exists a delta greater than 0 such that that implies this one. Okay, and that's this definition right here. Okay, now in this class, we're going to spend a little bit of time on limits, but that's certainly not going to be the emphasis. The emphasis here in this class is going to be more computational, not so much theoretical, but we'll do a little bit of computations. And so let me just show you a simple example of the limit, okay? So let's take the limit as z approaches 1 plus I of 3z plus 2I. Okay, now to find limits, it's it's significantly easier than proving it, right? As you probably know from calculus. To find it, you just plug in the point, right? So this, you can just plug in a 1 plus I right into there and distribute the 3. And then you get 3 plus 5I. Okay? But now, to prove it, as you know, is a little bit more difficult. But here's how I like to organize proofs here. I like to have the proof over here, the proof's over here, and then this is just going to be some scratch work. And if you're doing a limit proof, then the first thing you want to do is let epsilon be greater than 0. Okay, and that's, and kind of, you work backwards, but the problem is you can't write it backwards. You have to go forward. So, but because you have to work backwards, then you can put the backwards part here. So the first thing you want to do is you're looking at this right here. Okay, so you're letting epsilon be greater than 0. You're trying to guarantee this. You're trying to find, so what you're trying to do is you're trying to get a value of delta so that this forces that to happen. Okay, so that's the idea. Okay, so you just plug everything in. So this is our function right here. 3z plus 2y. And then our W0 is this right here. Okay, so the f of z is there. W0 is this 3 plus 5i. So you have that. Okay, now what you want to do is you want to try to simplify everything as much as you can. So use some, this is where the manipulation comes in. So we have 3z. Here you got 2i minus 5i, right? So you got a minus 3 there. This 2i minus 5i is minus 3i, right? Wow, everybody has a 3. So wow, that's fun. We can factor the 3's all out and end up with z minus 1 plus I. Oops. Okay, now if you have the modulus or absolute value of a product, so we have 3 times all this. If you have that, you can take the modulus of both of them, because so this turns out to be 3 times the modulus of z minus 1 plus I. Okay, and you can do that because that's one of the properties, because the modulus of z1, z2 is equal to the modulus of z1 times the modulus of z2. You're using one of the properties in one of those propositions. Okay, that's how you're getting that part right there. And then we just isolate this. Like that. And then this piece right here is exactly this. So z minus z naught in parentheses, less than that. This part, the z minus z naught, is this is z minus z naught. Z naught's right here because that's what you're going to. Okay, so that is z naught, and you can see that's z naught also, right there. So that's really good. So that means because of that, we know how to proceed. And the next step would be to choose delta to be epsilon over 3, or what's over here? Yay, we can choose that to be delta. Okay. And then we proceed to show this right here. Write down z minus z naught less than delta. That implies that z minus z naught is less than epsilon over 3. And then you just kind of work your way back up the list right there. Maybe you can skip a few steps here and there. Should be a plus. I put the 3 over and put it inside, and then that implies this one. And that implies this one. Which is it. And this is it, because this is your f of z, and this is your w naught. This is your right-hand side. This is your right-hand side. W naught, 3 plus 5i. F of z, 3z plus 2i is right there. So f of z minus w naught. And this is pretty much done. That proves it right there. Because you just proved that given epsilon greater than 0, there exists a delta. We showed that it exists by showing, there it is right there. It's epsilon over 3 will serve as the delta. It's going to be positive and it will work. And then we show that that implies that. Okay, so that's how you would prove limit. Okay, I wanted to do one other problem. No space there though, darn it. Okay, right here. I wanted to show you another, just to kind of work this out right here. So the limit as z approaches 3 plus 2i of okay, so here I did a different, I'm just right here, I'm just trying to show you that this is a different way of expressing the function. So this is a function expressed using the x and the y as opposed to the z. Okay, and I just want to show you to do this. So what you do is, in this expression right here, your x is 3 and your y is 2. Okay, because the x is the real part, the y is the imaginary part. And so what you're going to do is you're going to plug in a 3 for x and a 2 for y, and that's all you do. Okay, so I plug a 3 in for this x, I plug a 3 in for that x, and I plug a 2 in for that y. Okay, and I have 9 plus 6i minus 4, and so that's going to be 5 plus 6i. Yeah. Okay, so I just wanted to show you how to work with the other version, but we're doing a limit, but pretty much limits are kind of like plugging in stuff. Let's see here. Here's another proof in the examples that you can look at. Here's an example of a limit that doesn't exist that you ought to look at. Let me give you another example of a limit that doesn't exist. And I'll do it right here. Okay, let's take the limit as z goes to 2i of modulus of z squared minus 4 didn't write that right well. Minus 4, and then over z minus 2i. Okay, so here you kind of think this denominator doesn't look good because if you plug a 2i into here, you're going to get 0 in the denominator. So that's sometimes is kind of fun to do. Sometimes it's not any fun. Sometimes it's just weird. But let me show you that this doesn't exist. Okay, so to show that it doesn't exist, what you want to do is you want to split it up. You want to rewrite this. Instead of a z, write it as xy. So write it as like R2. And then you're going to 0, 2. Okay, so this is 2i is the same as 0. 2i has a 0 as the real part, and 2 as the imaginary part. So that's 0, 2, as far as x and y are concerned. And then you can also split this all up into x's and y's. The modulus squared is going to be x squared plus y squared. And then you have a minus 4 there. And then down here, this is x plus iy. So z is x plus iy. And then you got minus 2i. Okay, so that's because z is equal to x plus iy. That's what we're doing. Okay, so to typically show that it doesn't exist, what you want to do is you want to go along 2 different paths. So we're going to go along the path where x equals 2. And then we're also going to, then after that, we're going to go along the path where y equals, wait a minute, no, not x equals 2, it's x equals 0, because x is going to 0. Okay, and then y is going to 2. So this would be along the path y equals 2, like that. Okay, so we're going to first go along x equals 0, and then we're going to go along y equals 2. Okay, so that means that we're basically in this whole expression, we're just going to immediately force x to be 0. Okay, and then that means that instead of taking the limit as x goes and y go to 0, 2, it's just going to be y going to 2. Okay, because we just like made x go to 0 already. So we're just making y go to 2. Now, if you want to, if you think, you might think, well, that's kind of weird. How can you just like skip to the point? Well, I'm not really skipping to the point because the point 0, 2 is right here. That's 2i right there, right? That's the point 2i right there. By setting x equal to 0, I'm not skipping to that point. What I'm doing is I'm skipping to this vertical line here. I'm just skipping to the y-axis. And so I can still come in. I'm still not at the point. I'm just like coming in this direct along this path here, from the bottom and the top simultaneously. So it's kind of like that. Okay, so that's going to be the limit as y goes to 2. So I'm not setting y equal to 2. I'm just setting x equal to 0. So I'm not hitting that point. All these x's, I'm going to set those equal to 0. So we have y squared minus 4 up there, and down here we have I times y minus 2. Okay, now I'll give you guys a minute. I'll give you a few seconds. What do you think how do you think I should solve this now? If I want to find this limit as y goes to 2.
Factor it.
Yeah, factor the numerator into what?
Y plus 2, y minus 2.
Yes. And look at that, those guys cancel. And then you set y equal to 2, so you have, this is going to be 4 over I, which is the same as negative 4i. Okay, so that's going, so along that path, it's going to negative 4i. Okay, now I'm going to make this along the y equals 2 and make that blue. So here, I'm going to go ahead and set y equal to 2. And so then I'm making x go to 0. And what's happening there is that here's 2i. And I'm coming in along this path, like that. So I'm already making y equal to 2. So if I set y equal to 2 up here, then I have x squared plus 2 squared minus 4, and then I've got x plus 2i minus 2i. And let's see here. A lot of stuff's going to cancel. Look at this. 2 squared is 4, and then you're subtracting 4, so that's just going to all go away. And this is all just going to go away too, right? So we'll end up with x squared over x, but then one of those x's is going to cancel. You're just going to get the limit of x by 0 of x, which is just going to be 0. Okay, so this shows, because you get, for along this path, you get negative 4i, and along this path, you get 0, and those aren't equal. The limit does not exist. Okay, so this limit doesn't exist. And the interesting thing is that if you go along this path, you get a value, and along this path, you get a value, and so you're getting values when you're kind of doing your calculations. You're getting values, but then since they're different, then the limit just doesn't exist. Okay, and if you go in along different paths, then you can get different answers. Okay, so that's an example of that. Let's see here. What's the next? Here's another example right here of going along different paths and getting different answers. Here are some limit properties, and these are similar to limit properties that you would find in just regular calculus. Here, this is the definition of continuous. And it's basically, the main part is just this right here. This sentence right here. Okay. So don't worry about this other thing, isolated points and all that, whatever. Not worry too much about that. Those are just handling the technicalities. Mathematicians like to do. Okay, so then the next section is we talk about composition of complex numbers, and that pretty much just works out like how you'd expect. There's not much difference between that and the real numbers. I will say one thing though, this word right here, image, the image of a function, with complex numbers, it gets to be a bit more interesting, this finding image, because you can actually find images, they look more interesting. So like, for example, if I were to take, let me just show you an example of an image. So let's say I were to have the function z squared, okay, which is the same. If I put it in this form right here, in the polar form, and I square that, I get r squared e to the 2I theta. And just as a quick example. Now, if over here, let's say that I take this kind of piece of this pie here, Ooh, that's delicious. Right there, and I have this like wedge here, and it comes out to, let's say, 3. Okay, so this wedge here, you could describe it as the points re to the I theta, where r is between 0 and between 0 and 3. If I want to include the boundary, I'll go like that. And phi or theta is between 0 and pi over 4. So that's the image, right? So that's not image, that's the domain. Okay. And we'll call this the S. If I were to take f of S, as you can see right here, what it's going to do is each of these points in here is it's going to square the radius, and it's going to double the angle. So I'm actually ended up with this, e to the I phi, where phi is now between 0 and 9. And I mean, rho is between 0 and 9, and phi is going to now be between 0 and pi over 2. Okay. So I have this bigger piece of pi right there. So that's an example of the image of a function. So this right here, this is the image of S under F, under this function here. This is the image. So this is the image of this set. Another way would be to kind of express it this way. And there's your F. Okay, so that's kind of interesting. Okay, let's get on to the next topic. Derivative. So does this formula here look familiar? Yes, it looks familiar to everybody, right? It looks just the same as like the derivative with real numbers, except the x has been replaced with a z. And x0 has been replaced with a z0, and x has been replaced with z. Okay, but other than that, it appears to be the same formula, and it sort of is the same formula. Where this limit exists, then f is called differentiable. If you're differentiable at all points in an open disk centered at d0, then f is called holomorphic as d0. Okay. So if this is so G is like a set in the complex numbers. You could also, if you just think of this as just being C to C, I'm fine with that. No, I think it wouldn't make much difference. It's just a technicality. So you have the domain is something like this. You could have a situation where it's like it's differentiable on some line and not differentiable anywhere else. So then it wouldn't be holomorphic. But you could have a situation where you're differentiable right at a point, and then at a neighborhood around that point, you're also differentiable everywhere there. And that's called holomorphic. And so there's differentiable, but if you're differentiable in a neighborhood, then it's also called holomorphic. And then if you're differentiable in the whole complex plane, thing is called entire. That's where you're differentiable and therefore holomorphic in the entire complex plane. If you're differentiable everywhere, then it's entire. Okay, let's take a look at f of z equals z to the n, where n is a positive integer. Okay. And we'll find out where that's differentiable, and we can also figure out what the derivative is. So if z naught is any point in the complex plane, then its derivative is defined to be the limit as z goes to z naught of f of z minus f of z naught over z minus z naught. Yeah. And then we plug in the function here, which is z to the n. And then f of z to the n, or f of z naught is going to, I'm sorry, f of z naught is going to be z naught to the n. And then down here we have z minus z naught. Okay, up here, we're going to have z minus z naught. You can factor z minus z naught out. And then that's going to leave you with z to the n minus 1. Oh dear. Plus so if you multiply this with this, you're going to get z to the n, right? So e to z to the n minus 1 times z is z to the n. So then you multiply these two together, you're going to get this z minus z naught z to the n minus 1. But it turns out that if you add z to the n minus 2 times z naught, then when you multiply this with this, then this times this gets canceled out. So this times this is going to be the negative of this times this. That's just going to cancel out. And then z to the n minus 3 times z naught squared is going to knock out the other excess term. And then you're just going to keep going until you get all the way down to, until all the z's are gone and you just have z naught to the n minus 1. And then that last term will give you this, So this times this will give you this. And then everything else in between gets canceled out. Okay? And so these guys are just going to cancel with each other. And as z goes to z naught, then this goes to z naught to the n minus 1. And then this also goes to z naught to the, well, you have n minus 2 times z naught to the 1, which is also going to be z naught to the n minus 1. And so that's also going to be z naught to the n minus 1. And then this term is also going to be z naught to the n minus 1. And of course, you have n of those. There's n terms like that because it's going from, this is 0, 1, 2, all the way to n minus 1. So that means there's n of them. And that's the derivative. So the derivative of is n z to the n minus 1. And this sort of showed that it's differentiable everywhere because z naught's an arbitrary point. So this is entire. Okay, so you guys think you can memorize that formula? Of course, you guys already know that, right? It's just that the x's have been replaced with z's. Okay, so that's the derivative of any monomial. Okay, now right here, moving along to page 24. You have these properties here. And that basically, this allows us to do a lot of things. Like, for example, if you had, if g of z were, let's say, 3z to the fourth plus 2z minus 1, if it was that, then we already know that if you take the derivative of this, this is going to be 4z to the cubed. This is going to be just 1, right? The derivative of that's just 1. And so these properties allow you to just like basically just take derivatives as before. So that's going to be 12z cubed plus 2. That's going to be the derivative of g in this case. So it would be, namely, this property right here would allow you to do that. Okay. So ignoring, just like treating these as constants in the regular stuff. And then you have the product rule works, the quotient rule. And then this is what we proved already. And if the functions are differentiable, then they're going to be continuous. And then composition also. This is the chain rule. Okay, so chain rule. Okay, so all the properties of derivatives work from before but you have to be careful because this is in Z. If it's in X's and Y's, then it's not going to work that way. Okay, so if you see a formula of a function written in X's and Y's, then you can't, these derivative properties are not going to hold. Okay, so you can't fall back on your previous knowledge of derivatives. It's only when they're in terms of Z. That's when you can, and if it's in terms of Z, and it's not something like Z conjugate, because Z conjugate probably is going to be something that's not differentiable. And it's not in terms of modulus, because modulus is also going to be something that's not differentiable at all. But if it's like sine or cosine or a polynomial like this or something, then or an exponential function, e to the z, then and it's in z as opposed to x's and y's, or a combination of those, then it's going to be differentiable, and the formula is going to be the same as what you had before. Okay. Okay, so let's move along. This is proposition 211. This is kind of an interesting thing. So what happens here is if you have, let's say you have a couple of curves and they intersect, that's going to intersect at some kind of an angle, right? And if you have a function, okay, and if so if f is holomorphic at A, so that's a point A right there. If f is holomorphic and the derivative is not 0, then what's going to happen is these curves are going to map to something else, and this angle is still going to be the same. If you map these curves and they take the image of it, then the angle between the curves is still going to be the same. But you have to have f being holomorphic at A, and you also have to have the derivative at A not being 0. Okay, so so these are going to map to curves, and the new curves will have the same angle between them. And that's also, when that happens, that's also called conformal, so conformal mappings. Okay. So let's move on. Okay, the definition of one-to-one and onto. And the bijection is both one-to-one and onto. Let's not worry. Okay, we won't worry too much about that part though. Okay, so the Cauchy-Riemann equations. Now this part is quite important. So let me work it out right here. So if you have a differentiable function, let me kind of work it out over here. Okay. Cauchy-Riemann equation. Okay, I'll try to show you how to get these, how these work. Okay, so let's say you have a, let's say we have a function and the derivative does exist. We'll say f prime of z naught is equal, it's going to be equal to the limit as z approaches z naught of f of z minus f of z naught all over z minus z naught. Okay, so that's your derivative right there. So here we'll call that z naught right there, and that's going to be x naught plus I y naught. So another way of writing the derivative would be the limit as x y goes to x naught y naught. Okay, and then this would be f of x plus I y minus f of x naught plus I y naught. And that's going to be, down here we're going to have x plus I y minus x plus I y, x naught plus I y naught. Okay. Okay, so what we're going to do is first we're going to do what we did before. We're going to come in along this path right here. Okay, so the first one is going to be along, we're going to go ahead and set x equal to x naught and see what happens. So the derivative should still be the same thing, but it's going to be the limit as y goes to y0, because x has already gone to x naught according to this. Okay, and so the numerator is going to be hold on a second. I forgot one other step. It's really important. Back up a little bit. Okay, this is another important concept. This is kind of another important concept of complex numbers, that if you have a complex function in Z, then you can also write that in this way, as a real part plus an imaginary part. Okay, and so you have u plus iv minus u of x naught y naught plus iv of x naught y naught all over the same thing in the numerator. Okay, so you have this, and this is u of xy plus iv of xy. Okay, so if you go along on the red, then that's along x equals x naught. Then you're setting your x equals x naught already. So then you're going to have the limit as y goes to y0. And this is going to be u of x naught y plus iv of x naught y minus u of x naught y naught.
I'm not sure about that.
Minus I v of x naught y naught. I have that. And then down here, this is going to get wiped out. So you're just going to have I times y minus y0. Okay, so now it's going to be limit as y equals to y0. And then you're going to have u. I'm taking this and this. And then I'm taking this minus this. Over the same thing. This right here is actually negative 1 over, wait. It's just 1 over I, so I have this I right here, times the partial of u with respect to y. And then this one, the i's are going to cancel, and so this is going to be the partial of u with respect to x. Okay, and then if you go in along this path right here, along y equals y0, then you're actually going to get, u wait, this should be a y. Okay, you're going to get u x plus I Vx. If you go along the blue. I'm not going to do the calculations, but that's what happens. That's sort of the same thing that happens here if you is going along x equals x naught. Okay, so what's the point of this? Well, I'm probably not waste too much time. The point is this, that this right here, these have to be equal to each other. And these are both real, and these are both imaginary right here. So that means that ux must be equal to vy. And then here, because this is 1 over I is the same as negative I. So it's negative uy. So then what you have is that uy has to be negative vx. Okay, and then these are the Cauchy-Riemann equations. So this is, you need to memorize these equations right here, just this right here. Okay, and this is kind of how you get it, going different ways, just going along these two different paths. If a function is differentiable, then this has to be satisfied. And if these are satisfied, then, and plus another really easy to get condition, which is almost always satisfied, then the function is differentiable. Okay, at the point where these are satisfied. So basically, what you should look at it as is if these are both true, these equations are both true, then the function is differentiable. And Also, the derivative is going to be this. Okay, this is going to be the derivative. Okay, so if these equations are true, then this is going to be the derivative right here. Or you could say this is the derivative also, because they're going to be equal. But this is the more common way to look at it. Okay, so let me see, where are the equations? Yeah, so here, these are the Cauchy-Riemann equations. So ux equals vy, and uy is negative vx. So those are really important equations to satisfy. So let me give you an example of this. So let's say we have f of xy. So if we have a function, and this is x plus iy or xy, another way to write that. So if we have like x squared minus 3x plus y, and then we have plus I times a bunch of stuff, let's say maybe yx plus 2y squared. Then what you do is you identify the real and imaginary parts of the function. So u is going to be this one right here. And then v is going to be this right here. And then your Cauchy-Riemann equations are u x equals vy, and uy is negative vx. And this is the partial derivative. Okay, so let's see, what's ux? This is the partial of this with respect to x. So you treat y as if just a constant. Okay, so does anybody remember what the partial of this with respect to x is?
2x
Should have learned
equals
in,
3.
yes, 2x minus 3. And then the partial with respect to y?
X plus 1.
It's just going to be 1, right? Because those are going to be 0 and 0. Okay, what about over here? What's the partial? Wait.
I thought it's revi.
Yeah.
Yeah, that's a v right there. This one is 1, okay? But v, the partial here is what? With respect to y?
X plus 4y.
Yeah, x plus 4y. And then the partial of v with respect to x is
Y.
y. That's just it. That's why we're just y, right? Okay, so here, so what you would do is you would say, okay, these have to be equal, right? So 2x minus 3 has to be equal to x plus 4y. But then over here, these have to be negatives of each other. So 1 has to be equal to negative y. And which one is easier to solve, this or this? Come on, what's the answer to this? This one says, this one is just saying y has to be negative 1. Okay, so you need both of these equations to be satisfied. So now already y has to be negative 1. So let's put a negative 1 into here. That's x minus 4, right? And then this x can come over here, and it's x, and then this 3 comes over here. So that's -1. So this function that we have is somehow differentiable. This is already differentiable at the point -1, -1, and nowhere else. So it's only differentiable at that point. Okay, and because it's differentiable only at that point, then it's not differentiable in any neighborhood of the point. So it's holomorphic nowhere. Okay, so it's not holomorphic anywhere, and it's only differentiable at that one point. And the derivative is going to be the derivative at -1, -1. That's going to be ux plus I u. No. Dang, what did I say it was? Ah. Forgot what I said. Ux plus I Vx. So if I put a -1 in there, that's going to be what, -5? And then this one, if I put a -1 there, it's going to be -1, so minus I. So derivative is -5 minus I. Okay. So it's only differentiable at that one point. Okay, so this looks like a good place to stop for the day. So tomorrow we'll pick this, or not tomorrow, on Wednesday, we'll pick this back up. I believe you have homework assignment 1B, which is from chapter 1, that's due today. And then you have 1C due on Wednesday. So that means that Wednesday I can answer some questions on that if you want, if you have any trouble. Okay, was there any other questions before we end class for the day?
Yeah, well, how does it look like if it is not just differentiable in one point, like maybe 2 points? How would it look like?
That usually doesn't happen. Usually it's you mean if it's differentiable at lots of points?
Yeah.
Okay. That would be like if you took, let's take a really simple function. I'll do this really quickly. Let's take z squared. We know that's differentiable and the derivative is 2z, right? So if you replace this x plus iy, then you get x squared minus y squared plus 2xyi. Okay. So our real part is x squared minus y squared, and our imaginary part is 2xy. Okay, so ux is, what's ux?
2x.
Yes, and then vy is
2x.
2x.
is also 2x. Whoa, those are equal everywhere. Okay, what's uy?
Negative 2x. 2y.
Negative 2y. So y. And then what's vx?
2y.
2y.
2y. And so you have uy is equal to negative vx, and you also have ux equals vy. So this is satisfied everywhere. Okay, this is the function is entire. Well, all polynomials are entire and are differentiable everywhere. And also the derivative, you want to calculate the derivative this way. So I said ux plus I vx, right? So that's going to be vx is 2x, that's 2x. And then plus 2yi. I times Vx, so I times 2y, which is the same as 2 times x plus iy, which we already know is the same as 2z, right? So the derivative, we already know that 2z, right?
Yeah.
And that it's differentiable everywhere. So that's what it looks like when it's differentiable everywhere. They just completely match up everywhere, right?
Okay.